Okay, I think it's already 11:01. So while people are joining, I think we can get started. So I will do the opening as usual. So my name is Qiao, and I'm the organizer for this SIGCOMM Paper Reading Group. And this, I believe, is our 14th meeting. And we have in the previous meeting we have covered. I think for each week, for each of our meeting, we cover so far we cover different aspects in of networking research. And indeed we have covered data center networks, but in different perspectives, such as how to better support machine learning, in particular large language model training and serving and so on. But we haven't yet touched optical network data center networks made of optical switches. So it provides unique opportunities as well as challenges to support high throughput and low latency workload. Right. So this exactly is this paper is about. So the paper of the paper is called NegotiaToR, negotiator, right? So towards a simple yet effective on-demand reconfigurable data center network, and it was published at SIGCOMM 2024 last year in Sydney, and the authors are from Qinghua University, Shanghai University, and Huawei. So since this since this is an educational activity, so we have a PhD student from Hong Kong, Shaofeng to make the presentation first, and after that we are honored to having invited the first and the second author, Cong Liang and Xiangli from both from Tsinghua University as our guest of honor to join us for the Q&A and discussion. And during this phase, Qiang Su from Xiamen University will be the mediator. So this is a very wordy introduction, but I think I'm all out of words. So I think we can get started. So Shaofeng, you can have the floor. Thank you.
Okay. Yeah. Thank you for the opening. I'm the presenter today. So my name is Shaofeng Wu. I'm from the Chinese University of Hong Kong. So I'm currently a third-year PhD student. Today I would like to share the paper named Negotiator towards a simple yet effective on-demand reconfigurable data center network. So this is joint work by researchers from Tsinghua University, Huawei, and Shanghai Jiao Tong University. Let's get started. So firstly, some quick backgrounds. With more and more applications running in the cloud, traffic demands in data center networks are increasing rapidly, and traditional electrical packet switching faces capacity limitations in the post-Moore's law era, and the optical switching, which is high capacity and low cost, has drawn researchers' interest. So unlike packet switching, in optical switching, the topology needs to be reconfigured first before the sources need to send to a different set of destinations. And recently, AWGR-based technology has reduced this end-to-end reconfiguration delay to within 10 nanoseconds, which is sufficient for fast reaction to dynamic traffic patterns among TOR switches. And also, optical switching can be expanded to DCN scale. So for example, if we have very high port count AWGR, then we can use a huge AWGR switch to connect all TORs together. And but however, for low port AWGRs, which are more accessible, we can connect them using the thin cloth topology, which is a practical alternative compared to the to the parallel network topology. And for both topologies, the sources need to tune their wavelengths and send the data synchronously, and the data is forwarded to different destinations according to their wavelengths. And with the faster reconfiguration and the DCN scalability, we think the AWGR-based technology is ready for the data center networks. And the next question is how to schedule fast reconfigurable optical links. Here, the goal is about getting non-conflicting paths from the source to destinations, because optical links are bufferless, and the conflicts will lead to data damages. And we also want this scheduling to be rapid to enable fast reaction to the dynamic traffic patterns demands in data center networks, especially among TORs. So one of the existing solutions is traffic oblivious. which reconfigures the network according to predefined round-robin rules. This scheme is practical for industrial deployments, but however, due to the mismatch of the topology connectivity and traffic demand, it can actually suffer from sacrifice the latency and the throughput. Another solution is on-demand, which adapts the topology according to real-time traffic demands. This can potentially provide better performance, but there exists scheduling. There exists deployability and practicality concerns, mainly because of the fast on-demand scheduling requirements. A centralized scheduler can surely do the job, but will introduce excessive complexity. So this paper asks this question: is there a practical yet high-performance on-demand distributed scheduling architecture for reconfigurable data center networks? Solving this problem is very challenging. So firstly, scheduling itself often leads to more complexity. The measurements of traffic demands, especially flow-level traffic demand at the sources and the calculations like ordering by size at the destinations will lead to higher complexity, especially under the context of optical switching. And then to support a distributed algorithm, the TORs should frequently exchange scheduling messages with each other. And the control can use a separate control network to deliver these scheduling messages, but it will also lead to significant cost overhead. And finally, ensuring low latency for MICE flows, especially under incast, is not an easy work to do, because as long as the scheduling delay exists, MICE flows cannot be sent timely, and this will lead to downgraded latency. And considering deployability, this paper presents NegotiaToR, an on-demand, reconfigurable DCN architecture towards a simple yet effective design. And regarding the three challenges we have mentioned, the author presents three designs in NegotiaToR. The first design is NegotiaToR matching algorithm, which is tailored towards on-demand scheduling on flat topologies. And the second design is using two-phase epochs to support inbound pipeline scheduling and one-hop data transmission. And the third is a mechanism to bypass the scheduling delay for flow completion time optimizations of MICE flows. And then I will firstly discuss the NegotiaToR matching algorithm. So basically, there are two kinds of conflicts when scheduling the optical links among TORs within a flat topology, which are one-to-many and many-to-one conflicts. And this is actually a matching problem, and similar problems have been seen decades ago in crossbar packet switches, wherein switch need to get non-conflicting input-output pairs to forward data packets or data cells. Actually, many works have been done in this area and have been proven to be fast and practical, along with extensive implementation experience. And the NegotiaToR matching algorithm used by this paper is inspired by one of these works named RRM, and focuses on TOR level matching on flat topologies. And to understand how NegotiaToR matching algorithm works, so we can let's first see an example on the parallel network topology. So in the parallel network topology, each port can receive from all TORs, and the target is to choose one source from all the possible sources for each of the ports on a TOR switch. And since each TOR switch has many ports, all ports on TOR switch need to be scheduled simultaneously. And now let's assume an example. So here we assume that TOR1 has traffic to TOR2, and TOR3 has traffic to TOR2 and also TOR4. The first step of the matching algorithm of NegotiaToR is TOR level request. So in this step, the sources check their local queues and send the boundary request to destinations with no data size or priority information. And then the second step is called port level grant. In this step, the destinations are aware of multiple TOR requests, and they need to resolve the destination side conflict. And to resolve this, a grant ring is utilized to ensure the fairness and also non-conflicting port assignment. So basically, the grant ring will work like this. So the pointer of this grant ring will indicate the source with the highest priority from all sources, and the priority will diminish in a clockwise direction. So after granting one source, the pointer is updated to the next position. And this grant ring-based scheduling will effectively ensure fairness while avoiding a starvation in port allocation. And to further improve the fairness, all ports in TOR2 will share the same grant ring, and TOR2 can utilize this ring to allocate requests to all of its ports in turn. And as for the TOR4, since the process is similar, but since there is only one request, so which is the request from TOR3, so it just allocates this request to all the ports, and then the port level grant, this step is over. After this step, the destinations will send the grants back to the sources. And after the sources receive this port grant, they are aware of the port grants from multiple destinations, and they are also aware of the potential conflicts. And to resolve this source side conflicts, they will use per port accept ring to choose one grant for each port. And this will mark the finish of one negotiator matching algorithm scheduling process. So after these three steps, so which are TOR level request, port level grant, and port level accepts, the sources will tune their wavelengths according to the locally derived scheduling results, with no need for the result delivery. And the negotiator matching algorithm can also be adapted to other flat topologies. For example, in the thin clause topology, because the first so for example, in the thin clause topology, a port can only receive from a subset of the TORs. So the author modifies the grant ring to match the topology connectivity. So for example, here, because the first port of TOR3 can only receive from TOR1 and TOR2, so it is given a per port grant ring with only TOR1 and TOR2. And similar for other ports, they are given the grant ring according to the sources. And in this way, negotiator matching algorithm can be adapted to the thin clause topology. And now we have the negotiator scheduling algorithm. And to enable its running, we need to provide full match conductivity among all TORs, because they need to exchange the scheduling messages, including those request, grant, and accept with each other. So, and following previous practices, the author used a round-robin reconfiguration to work as full mesh to do this. And one of the intuitive solution is shown here on the slide. So as you can see, so firstly, the network will reconfigure itself according to the round-robin rules, and the sources can then send requests to the destinations. So however, the destinations cannot receive the request immediately, because there exists a one-way delay between the TORs, so which is typically several microseconds. And such delay also exists between the grants and the accepts. And due to strict front-end dependencies of the request, grant, and accepts, the sources can only wait during the one-way delay. So, and this will lead to link waste and downgraded goodwill. And to address this and avoid wasting the link capacity, so instead of running only one scheduling process at the same time, the authors run three of them simultaneously. So this means that the nth request and n-1th grant will be transmitted right before the n-2 data transmission. And the n-2 data transmission can leverage the one-way delay of the nth scheduling process. So as you can see in the figure, and this will avoid link bandwidth waste. And based on this pipeline scheduling design, the TORs in the negotiator run synchronously in fixed time intervals called epochs. So for each of the epoch, it is composed of two phases. which are the predefined phase and the scheduled phase. So in the predefined phase, reconfigurations will happen very frequently to provide predefined connections and to support pipelined distributed scheduling. And in the scheduled phase, the connections are fixed based on the locally derived scheduling results to provide on-demand connections and support data transmissions through one-hop direct path. And now with the pipeline scheduling, links can be better utilized for higher throughput, but as for the latency, mass flows can still suffer from long scheduling delay. And to understand this, we can still look at another example. So suppose here there is a source destination TOR pair that had no traffic to send before, and after new traffic arrives, it requires at least 2 epochs before the request can be accepted. And this is even the lucky case, and the scheduling delay will be longer when conflict happens in unlucky cases. And for mass flows, this will lead to long flow completion time, especially under incast scenarios, which will adversely affect the application performance. And to address this, the author asked a question. So if they can bypass the scheduling delay for mass flows, so their FCT can be optimized. And this leads to the third design of NegotiaToR, which is the scheduling delay bypassing mechanism. So we can recall that in the predefined phase, full mesh connectivity is provided to support exchanges of scheduling messages. And actually, this is a perfect opportunity if there exists some urgent data to send. So therefore, the authors utilize this full mesh connectivity during the predefined phase by piggybacking small data packets along with the scheduling messages, and this will get this kind of guaranteed and scheduled transmission are sufficient for mass flows because they are small in size. However, with piggybacking, there is one problem still exists because the elephant flows in the source TORs, so whose FCT is not the main concern, may still block the mass flows data and occupy precious unscheduled transmission opportunities. And in this case, the author maximized these opportunities that mass flows can be scheduled by prioritizing mass flows at the sources with existing approaches such as PIAS. And you can refer to the paper for more details if you are interested in this related work. Yeah. And actually now the main design of NegotiaToR has been fully presented. And the author also emphasized the design efforts towards deployability and the practicality of NegotiaToR. So I will also introduce them in today's presentation. So the NegotiaToR matching is actually inspired by RM. So therefore, it is possible to borrow the proven implementation strategies directly from them. So for example, using a programmable priority encoders to implement rings for the matching algorithm. Also, other designs like no iteration, no data relay, binary request, and stateless scheduling all contribute to reduce complexity in implementation. Yeah, and these techniques are simple, and that's good. But one question is that would a more complex design significantly improve NegotiaToR's performance? So in the paper, the author conducted some discussion on the design choices of NegotiaToR. I will list one example here. So one of the example is that, so what if iterative scheduling is used, and because iterative scheduling is actually a practice in crossbar switches. So basically, it is easy to think that you can use iterative scheduling also for NegotiaToR. The author showed that actually this is not a good fit because NegotiaToR has a longer delay between consecutive steps. So when there is no iteration, it only requires 2 epochs for the request to be scheduled. But when there are 3 iterations, this becomes 6. So during long scheduling delay, data corresponding to the request may already be sent, leading to outdated requests and possibly downgraded performance. And the author have already confirmed this with experimental results in the paper. And yeah, and for other explorations and design choices, you can refer to the paper for more details. Yeah. And for the evaluation part, I will briefly introduce the main evaluation results of NegotiaToR. The author conducted simulations that contain 128 TORs, which are connected by two representative flat topologies. For practicality, the results with mass flow without mass flow prioritization is also shown on the figure. As you can see, so in the results, it shows that the NegotiaToR can achieve both small mass flow FCT and high throughput on two representative flat topologies. And particularly, the mass flow FCT is orders of magnitude better than the traffic oblivious spin. And to sum up, so this paper presents NegotiaToR, an on-demand reconfigurable data center network architecture towards a simple yet effective design. The author presents NegotiaToR matching algorithm, which is designed towards minimalist on-demand scheduling on flat topologies. The author also used two-phase epochs to support in-band pipeline scheduling and one-hop direct data transmission. And the third design, the author also provides scheduling delay bypassing mechanism for those mass flows by piggybacking small data packets together with the scheduling messages and to optimize the mass flow FCTs. And by leveraging the faster reconfigurable Opti-1 hardware, NegotiaToR is expected to facilitate the development of next generation of reconfigurable DCNs. And this is all of my today's presentation. And thank you. Yeah.
Yeah. Okay. Cool. Thanks for the great sharing, Shaofeng. So next we will move to the discussion part. So today we have a great honor to have the first author Cong here to share his insights and experiences about this work. So does anybody
Thanks for inviting us.
Yeah, does anybody online have any questions? You can just say it or type it in the chat box. So I will introduce the question.
Can I ask some questions first? Actually, I have some questions.
Sure.
Yeah. So thanks for this work, and I think this work is very interesting. So even though I'm not an expert in the optical switching field, but basically I can understand your designs pretty well. And I have two very high level questions for this work. The first question is that basically optical switching is expected to provide higher bandwidth, better performance compared to those electrical switching based techniques. But I'm wondering, so if the reliability of the optical switching devices, so if the reliability is better or it is worse, or do you have any unique failures that will happen on optical switching techniques? Yeah. So this is my first question, and you can I will ask another.
Yeah. For this question, actually, recently I'm also investigating some works on reliability, and I think you may know this. When we use transceivers, it's actually highly unreliable compared with cables. But they do have many advantages. Like you mentioned before, they can provide higher bandwidth with lower cost and with lower power consumption. Yes, and so we think it is a great technology when we face higher gap between the switching demands in the data center networks and the actual switching capacity of data center electrical switches. It's a very promising technology. So we decide to look at it and see if we can design an architecture that makes the most of the most advanced fast switching optical hardware. And for reliability, we do have some designs regarding failure handle the failure cases. But I think if in the future, if the reliability of the optical hardware can be better, then the negotiator can also benefit from it.
Yeah, that's cool. Yes. So actually,
following this question,
I have a question.
sure.
Why for electrical switching there is capacity limitations post Moore's law? What is the relationship between Moore's law and capacity limitation for electrical switching?
So the question is, if I understand it right, the question is, why do we think the traditional electrical packet switching is become insufficient for data center networks?
Yeah, yes, but why you think Moore's law has anything to do with it?
Yeah, I understand. Yeah, the thing is, actually, this is the trend of recent researchers. We think that because the slowdown of Moore's law, in electrical packet switches, we rely on switching chips, which is based on CMOS technology, which is manufactured with CMOS technology to forward the packets. So with the slowdown of Moore's law, such switching chips are getting harder and harder to get more switching capacity with the acceptable power consumption and the die area. That's the connection between the slowdown of Moore's law.
So it is not bandwidth limitation; it is switching limitation.
Yeah, it's the limitation of the switching chip itself.
Yeah, so it's not really. So what do you mean by capacity here? You mean capacity of the switching or switching ability to forward traffic at higher rate, right?
Yes, like 51.2 Tbps, like that.
Exactly. Not really related to the bandwidth of the link.
Yeah,
Right?
not that.
Exactly. I got it now. I agree. I agree with you.
Yeah.
Thank you.
Yeah, thank you for your question.
yeah, cool. Yeah, and following my first question, actually, so I think failure is one of the key problem that you will see in the like AI training and inference. Yeah, because in AI training and inference, failure is very important. Like link failures, you can get like asymmetric topologies, and you will cause performance downgraded performance. Yeah, and so my next question is that so in your opinion, do you see any specific challenges that if you want to use optical switching for AI training networks, especially those internode communications? Because actually I see in recent SIGCOMM publications, there are some people doing optical switching based HBD, so basically high bandwidth.
Yeah, I saw that paper.
Yeah,
it's a great paper. It's very interesting.
Yes. So do you see any challenges and practical challenges if you want to use optical switching for the internode communication in AI training? Yeah. Thank you.
Yeah, okay. I got your question. And this is a very interesting question. You may know that Google has published a series of papers showing that it has changed its core switches into optical ones. Yes, and that's not for AI training, that's for traditional tasks. But in AI training, the workload is much more predictable than before. So the chances or the opportunities that we change the top layer switches to optical ones is much higher. So it can because the scheduling efforts, the traffic engineering efforts will be lower than before than the traditional compute tasks in AI training tasks now. And so I think firstly, we in the era of AI training, we can of course change the core switches to optical switches to get more bandwidth. Yeah, and also optical switching, because we can reconfigure the links during training or inside training jobs using optical switches. So I also see people are using it for failure handling. I'm not sure if you had read that paper. I think it's NVIDIA. NVIDIA published the paper on this. The basic idea is you can add a layer of optical switches between current TOR switches and aggregation switches. Like you add an optical layer, and once, for example, once aggregated switch is broken, you can dynamically reconfigure the OCS, the optical switches, to like connect the QR to another healthy aggregated switches. Yeah, so you can also use the optical switches to do failure handling. That's also a very promising direction. And if we can get more advanced faster switching hardware like used in NegotiaToR, we can also introduce some like inter-iteration reconfiguration. But that's another topic. That's also very, very promising. So to conclude, I think in AI training, we can, of course, bring optical switching into the cluster, and there are many exciting opportunities.
Okay. Yeah. Thanks for us. Yeah.
Thank you.
Yes, cool. Following Shaofeng's first question, I'm just wondering if there is some software-based fault tolerance approaches to ensure the reliability. Considering, actually, I think it is impractical to design a completely reliable hardware in the data center architecture, right? So we still need to design some fault tolerance mechanism upon the optical switching. My question is that will there be any difference between the fault tolerance mechanism in optical switching and traditional architecture?
Okay, this is a good question. And when we look at NegotiaToR, we actually have a serious failure tolerance design. Like we utilize the predefined phase, because in predefined phase, each node will communicate with all other nodes. Yeah, if one node found that it didn't receive any messages, even dummy messages from a specific port, then it think, oh, maybe this port is broken. Then it will dynamically adjust the scheduling results to avoid using that port. Yeah, this is in NegotiaToR, we did that. And there are also other designs. For modules, we can check the paper. And as for optical switching, I think there might be more opportunities, because firstly, we now have the ability to adjust the link. Like before we discussed with Shaofeng, we can actually use OCS, use this hardware to bypass the 3 field nodes. Yeah, and as for software-based solutions, there are some papers focusing on routing in optical data center networks. Yeah, like the paper UCMP from also from SIGCOMM 2024, and it gives you a set of paths that you can choose. And if some path has some link broken, then we can choose another path. Yeah, so we can also use that to avoid the faulty links or faulty ports. Yeah, so I think that is the software-based solution. I'm not sure if this answers your question.
Yeah, I got you, but following this, will that incur some load balancing problems?
Load balancing,
Yeah.
yeah, yes. I think to avoid a faulty node or a faulty link, we will like the load balancing. I think it will be affected, but we may have to do that. I'm not sure.
Yeah. Actually, yeah. Recently, we are working on some load balancing work
Mhm.
for LLM training. So
Yeah.
we think considering there are many links, many available links in the Natch cluster. If there is some single point failure, our experiments show that the load balancing can be still well for just single point failure. So I'm just wondering if we choose the optical switching cluster, will the load balancing problems be the same? Yeah, that's
Yeah.
why I asked this question. So
yeah, I think the hardware level reconfiguration ability will make the failure handling process easier. So yeah, that's my opinion. I think for failure detection or for failure handling, optical switching actually can bring us more opportunities.
okay, cool. I got you. Oh, we got another question from the chat box. Yeah, so let's see. The Chen Xin is asking if the current optical switches are fixed functioned. So if it will be reconfigurable and programmable in the future, similar to the Tofino switches.
Yeah, this is also a very interesting question. And well, now I think currently the optical switches are more like it just does simple forwarding, or I'm not sure if we can call it forwarding or not, because it just connect. You can think it just connect an ingress port to an to a egress port. It just does that, and the data can be sent through this fiber through this physical link. But in the future, I believe we can, of course, integrate some like computational power into it. Like I know there are some work on optical calculation or optical compute now. Optical compute, you can actually use optics, like use its amplitude or physics or something like that to help you calculate something to help you do like add or minus or multiply things like that. And if we can integrate that kind of function into current optical switches, I think they can, of course, do much more things. Like we can use optical switches to do in-network computation, like what we can use P4 switches to speed up the ML training process now. It's very promising and it's also very interesting. Yeah, but for now, I think it's more like a simple or basic forwarding.
Just to add on that, do you know if it caused additional delay if the optical calculation, how much of additional delay that would make?
Yeah, I think if you are interested, you can check a paper. I think it's called Lightning. It's from Zhizhen Zhong and Professor Maya Gobadi from MIT. And I think you will find some specific data there. Yeah,
All right,
thank you.
thanks. Thank you.
Cool. Any other questions?
Yeah, Chang, I have a couple of questions. So, what I'm wondering, I think probably most of the audience are not expert on optical switches. So, I think this paper certainly gave us a lot of valuable information, a lot of new information for us to learn. But I'm wondering, in your design, how well I think in terms of scheduling, you are essentially using this distributed scheduling. But so does that mean it has no scalability bottleneck, or there is one? We just didn't see it in the presentation yet.
Yeah, this is a great question. And as for the scheduling logic, we think it might not be the bottleneck because it is inspired by RM, and we already have many implementation experience, and we can just take that. And I think from my perspective, I think the scalability bottleneck of NegotiaToR comes from its the predefined phase. Because in the predefined phase, we have to use round robin to connect every pair of TORs. And if we have many TORs, this means the round robin phase will be very long. And to reduce the duration of the predefined phase, we can use more optical switches, make the TORs to have more ports and connect it with more optical switches to shorten the round robin phase. And if we do not do so with many TORs, with more TORs, the predefined phase will be long. And if the predefined phase is very long, like even much longer than the scheduled phase, then the network will be degraded to pure round robin with no valence load balancing. And at that time, the goodput and the FCT of this system will be much worse. So yeah, I think the challenge, the bottleneck of scalability of NegotiaToR comes from the predefined phase. When we connect more ports, like many ports together with NegotiaToR, we will want to use more uplinks for each TOR, use more optical switches to shorten the predefined phase.
I see. So, just out of curiosity, like I said, I'm not the expert, but how often do you have to go through this predefined process?
Yeah, for our paper, the whole epoch, I think I can get some specific data now. I think it's just, it's not on the slide, but it's in our paper. For the setting in our paper, we are using 128 cores, and for each epoch, we have the predefined phase of I think it's around 0.96 microseconds, and for the schedule phase, it's 2.7 microseconds. So the whole epoch is around 3.66 microseconds. So for the experiment set up in our paper, we will have to experience a predefined phase every 3.66 microseconds.
I see. I think there's another question from the audience, but let me just throw in very quick follow-up one. So you mentioned that this, like you said, you mentioned this predefined phase. It may encounter scalability bottleneck as the number of core switches increases. So since this, is it possible? I'm just like I said, I'm definitely not an expert. So is it possible that some pre-computing can help? Basically, if you could pre-compute maybe most of the cases, or maybe even half the cases, would that help? Basically, alleviate this bottleneck.
Okay. The reason that we need a long predefined phase, we need to make sure each pair of TOR gets the opportunity to connect with each other. Is that we want to provide opportunities for TORs to send and receive scheduling messages from all other TORs. So we have to make sure every pair of TORs connect with each other. And that will take time because reconfiguration will take time. It will take like the most advanced hardware can make this reconfiguration delay to around 10 nanoseconds. But even with that, even we do not send any data cell in the predefined phase to round robin 128 TORs, it will still take some time. Yeah. And to make sure the system can react to real-time traffic demands, I think we have to do that. We have to make sure each TOR can get connected with each other. But recently, also a paper from SIGCOMM 2024 called Qinghua. It's also a paper on reconfigurable data center networks. It's also very interesting. It brings up an idea that we can. It's an semi-trafficably with reconfigurable data center network. It shortens the round robin phase by groups or groups nodes that need to frequently send the data to each other. And only these small groups, only nodes inside these small groups need to experience the round robin process. And I think maybe we can borrow that idea into NegotiaToR, like that works to shorten the predefined phase. This is also a promising improvement.
Yeah, I agree with you. Yeah, I think that's definitely promising. Basically, by shrinking the scale of the problem, you only let a small number of groups or switches to go through this predefined phase. That you won't have to suffer from the scalability bottleneck. Yeah, I think that definitely makes sense. Yeah, great.
Yes.
Okay, so sorry to hog in the microphone for so long, but I think Cheng, you can read the question from Xuan from the chat box. Thanks.
Yeah, sure. Xuan is on the chat box. The question that in systems like RotorNet and Opera, the mice and elephant flows are handled separately. So RotorNet combines optical and traditional switching, and Opera leverages one hop versus two hop paths. So could NegotiaToR also be extended to explicitly separate mice and elephant flows instead of relying on the piggybacking? Would that help improve performance on the dynamic traffic?
Yeah, okay. Thanks for asking. And RotorNet and Opera are both very, very interesting work. And RotorNet is from SIGCOMM and Opera is from NSDI. And basically, Opera is an improvement of RotorNet. I think Opera actually use one network to handle mice and elephant flows at the same time. Yes, they are handled separately, but they are handled in the same network in Opera, just like NegotiaToR does. And I think the main difference of Opera and NegotiaToR's design choice comes from the fact that Opera and RotorNet, they are based on a commodity switching hardware. And for them, we can only use the optical switches that have a reconfiguration delay for like tens of microseconds. And NegotiaToR is different. When designing NegotiaToR, our goal is to make the full use of the recently developed fast switching optical hardware with like 10 nanosecond reconfiguration delay. So for NegotiaToR, we can actually use the fast switching capability of new hardwares to handle elephant flows and mass flows at the same time with the same network using the same mechanism, like one-hop transmission and distributed scheduling. We do not need to handle them with different mechanisms or different networks. So for NegotiaToR, to conclude, for NegotiaToR, our goal is to makes a full use of the newest hardware and use the faster switching capability to try to use one network, one mechanism to handle all flows, including mice flows and elephant flows. Because if we have such hardware, if we can use one mechanism and one network to serve all flows, then the maintenance cost, the cost of running this system will be lower. The operational cost will be lower. That's one of our goal. So that's why we use different design choices than Opera or RouterNet.
Yeah, the following question. If we pipeline the request grant accept process, how much performance improvement can we expect in terms of scheduling time?
Okay, if we pipeline the request grant accept process. So now we are actually, we are pipelining the request grant accept process. Compared with no pipelining, we can see the previous slide. Yeah, this one. So if we are not pipelining request grant and accept, the scheduling delay will be this long, like shown in the slide. And the main point is not the scheduling delay. The main point is the wasted links between the first round robin phase and the second round robin phase, and also the third round robin phase. So when we are pipelining the scheduling process, the scheduling delay remains the same. We still need like around 2 epochs to get the scheduling result. The difference is we are actually fully utilizing the network. So if we do not pipeline the scheduling process, then due to the large one-way delay between 2 hours, then the network is idle during the 2 round-robin phases during the one-way delay. But if we pipeline them, then the network is fully utilized. So the main difference is actually good put, not the scheduling time. I'm not sure if yeah, thank you.
Yeah, that definitely makes sense. I actually have another high-level questions. So, considering the advanced performance of optical switching, so what do you think is the best way to move from the traditional switch-based DCN to the optical switching-based DCN? The best way to go from the traditional one to the next generation.
Yeah, so how to fluently do the transition from traditional data center? Yeah, I think Google has done a very great job. And in its SIGCOMM paper Jupiter Evolving, it shows the process of how to gradually replace the core switches from electrical switches to optical switches. This is the gradual process. You can, for example, you can change one core switch to optical switch at a time. You can change them one by one. You do not have to change them all. So we can actually use a hybrid data center network to connect the nodes. Yeah. So we do not have to change all the network devices. And even for negotiator, things are still the same. We can actually, as mentioned by the chat box before, we can make TORs connected to 2 separate network, and one is the optical switching network, and the other is the traditional electrical switching network. That is also a choice.
Yeah, does it require changes on the end host network stack?
Yeah. I think it. I think it does. Like for TORs, if we connect the TORs with two separate network, like one optical network and one electrical network,
Yeah.
then we first need to decide which network we want to choose to send a specific like a block of data. If this data is from a mass flow, it cannot wait for reconfiguration delay, then we can send it through electrical network. But if the data is the bulk data, like it's very predictable, and we can establish the OCS link in advance and send the bulk data with high bandwidth provided by OCS, then we can send it from the optical network. So at least we need a mechanism to split the traffic to the two networks. Yeah, and also for optical switching network, there are also some work on how to optimize their optimize their transport layer. There are some specific transport layer design for optical network to handle its like reconfiguration process, and that's also a different. Yeah.
Yeah, that makes sense. So what do you think the how huge the engineering effort for the data center operator?
Yeah. So I think some company like Google have already explored a lot on this. Like they are actually using optical switches, optical network to train large language models, like they presented in TPOV4. Yeah, and they have already developed the whole technology stack, including the controller, including the switch, optical switch hardware. And I think based on such explorations, even though for now it's hard for individual operators, individual data center networks to suddenly transit from the traditional network to the optical network, but with more explorations, I think in the future this transition will be more fluent, and the operational cost of optical networks will be lower.
Yes, cool. Yeah, that's promising. So,
yeah,
we are almost the time is almost up. Just last question. For a new student who is not familiar with this field, so what would be the best way to get started?
Get started with optical network, optical switching.
Yeah.
I think for students, because actually for now, the companies all in the industrial industry, the companies that are using optical switches are actually not that many. It's still a new area. So we can, as students, we can start from reading papers from like SIGCOMM and NSDI. Recently, like especially in SIGCOMM 2024, there was a whole session for reconfigurable networks, and there were 4 papers, and maybe we can start from that, from the classic papers like mentioned in the chat box, like RotaNet, Opera series. Yeah, we can start by reading papers as a student. That's my suggestion.
That's cool. Yeah, I agree with you. Yeah, so time is almost up. So it's 12 o'clock. So we are coming to the end of today's meeting. So let's give a big thank you to Shaofeng for the wonderful presentation, and also to Cong for joining us to share his experiences. So it was really great to have you here. This paper actually brought up a lot of interesting points and sparked. I think we have 40-minute discussion. So definitely gave me a lot to think about. I think everybody here also learned a lot from our discussion and presentation. So yeah, thank you all again for joining today's reading group. So hope you enjoyed it and got something out of it. And yeah, of course, we'd love to see you again in our next SIGCOMM reading group. Yeah, so all right, that's it for today. So good night and have a good day. See you next time. Yeah.
Thank you.
Thanks, Tom.
Yeah,
Thanks,
thank you.
Shaofeng.
Thank you.
Yeah, thanks.